Welcome. So what I want to do is just kind of give you a little introduction into logarithm graph and kind of see where it comes from. So far what we've talked about is our exponential graph. And our exponential graph had y equals a real number a raised to the x power. And what we talked about with this is obviously the base is going to affect our graph and how quickly it's going to increase or even decrease, depending if it's a growth or a decay problem. However, when we're just dealing with an exponential growth problem, we know that all of them are going to cross at my intercept at 0, 1. And then also, when creating a table of values, so we have y equals a to the x. Well, if I want to create a table of values, we know that when obviously x equals 0, we're going to have 1. And then if x equals 1, we know that we're going to have our value of a. All right? And that was just kind of some very similar points that when we plug them in, we can at least find 2 points to graph it and then get a similar transformation. Then what we could also look at is when graphing exponential, is we applied our transformations, shifting the graph left, right, up, down, reflecting over the x, reflecting over the y, and also talking about not just so much exponential growth, but exponential decay. So now to introduce you to what we're going to now talk about is logarithmic. All right, and logarithmic is going to come from finding the inverse of our exponential. So what I'm first going to do is show you what to do for that algebraically, and then start going into it graphically. So if I was going to solve this, solve by using the inverse, one thing hopefully you guys remember when determining the inverse, what we do is we swap the x and the y variables. So I'd say x equals a to the y, and then we solved. But we kind of come into a problem here is how we're going to solve when we have y raised into an exponent. So what we did is that's where we kind of create into our formation of the logarithm. And that's exactly what a log is going to represent. If I rewrite this now as y equals log base a of x. All right? So what exactly this equation is telling us is that is what we call the inverse of y equals a to the x is y log base a of x. And what a logarithm again states, and I have a couple of other videos going through that, is a raised to the y power equals x. All right, so that's exactly what your logarithm is going back and stating. So now let's go and take a look at what the graph is going to be. All right, so when we're looking at the graph, here's your exponential function. If you guys remember graphing a function and its inverse, one thing that we notice is a graph and its inverse are reflected about the y equals x line. So if I was going to take this exponential function and I'm reflecting it over the y equals x line, what I'll notice is my graph is now going to be reflected. So instead of having a point at 0, 1, I'm now going to have a point at 1, 0. Instead of having a point at 1, a, I'm now going to have another point at a, 1. All right, so the graph's going to look something like that. And again, it's really going to depend on how fast it's increasing or decreasing based on the transformations and also the base of your logarithm. So let's go and talk about a little bit about some of the features of our exponential graph, and then talk about how those are going to relate to your logarithmic graph. So the first thing we want to talk about with exponential is the asymptote. Remember, this is the line that my graph is going to approach. And we write that little asymptote as that nice little dotted line. And that asymptote for an exponential function is y equals 0. When we're talking about our domain, we notice that this graph is not restricted on the x-axis. So our domain is from -infinity to infinity. But our range is restricted to only positive numbers for the growth for looking at this. So therefore, it's going to be 0 to infinity. Now, in talking about the asymptotes, the range, and the domain for a logarithmic graph, you can see that this graph is not exactly the same. And since we're asymptotes, if I have this asymptote being reflected over this line, what that's now going to change is now I'm going to have a vertical asymptote. And that's going to be what my graph is going to approach. So in talking about the vertical asymptote, I can say this graph has an asymptote of x equals 0. The domain, you can see that my domain is now restricted. It doesn't contain all real values, but now it only contains values from 0 to infinity. And the range all right, is now going to contain values. Instead of from 0 to infinity, you can see my range. This graph is going to infinitely increase and infinitely decrease. So my range is from negative infinity to infinity. All right. So ladies and gentlemen, that's just kind of the basics of the information of going from exponential to logarithmic. We can take a look at it by algebraically determining the inverse and showing our logarithmic notation, but also just taking a graph and the information from it and finding the inverse and then just taking a look at those. And remember, when we're looking at a graph and its inverse, it's pretty much just being switched around as far as the information and also as far as on the points. So there you go, ladies and gentlemen. Just wanted to kind of give you a brief little information on that, and I hope you enjoyed. Thanks.